class, we are now starting chapter 26.1 and 26.2. I'm just going to briefly discuss 26.1. We're going to get more into this. So we look at two jewels here. We have an emerald and we have a ruby. And the colors of what we see with this has to do with the d orbitals. So first of all, it starts with the fact that there's a host crystal and there's an ion in it. In this case, there's a chromium ion in both of those. But when we expand out on this, it's not just the ions. It has to do with the d orbitals and how they split apart. That's going to introduce us into crystal field theory later on in the I believe it's the last section of this. And that is how we see the colors in these jewels and other jewels. So I'm doing a quick overview, but this is going into, we're going to go into that section later. So properties of transition metals. This is mostly just a review right now. So the properties of transition metals, if you remember, they're very different. We don't include them in main group metals, and that's in the middle part right here. And which is this yellow green color of all the colors they could pick. That is wonderful. Excuse me. They have high melting points, high densities, moderate to extreme hardness, and they're very good electroconductors. Remember, we're still dealing with metals. They are just different from the other ones because they have different oxidation states. There's differences that vary, that they don't really necessarily follow the rules of main group metals. The similarities come from similarities in the valence electron configuration, which we're going to go over as well a little bit. So if you remember, hopefully you remember doing this in 110 and I believe 111, but you definitely learned it in 110. And this is basically the electron configuration. This is the orbital filling, where you would make these half arrows as electrons and you would fill them up based on the atomic number. Now, when it's a stable atom, it has the full configuration of electrons. When we either add electrons or take them away, they become ions, and it's either a cation or an anion. These being metals, they tend to have a higher affinity to lose the electrons. That makes them more stable than actually taking one on. And in some cases, they don't even have, they have filled electron orbitals that they wouldn't even be able to take electrons in. Okay, so electron configurations of a D. Now, in your book, it shows this n minus 1 and so forth. So I want to make sure people understand what that is. Remember, n is the quantum number, and that's the rows, which I don't think I should have put it here. Remember, the number here is the representative of the period number, but that's also the quantum number, and that's the one that goes across. So that would be n equals whatever it is. So that's what the n is right here. That's any of the numbers. So anything here would be 1s, 2s, 3s. That's the n number. Now anything in the middle, remember, is one less. That's what this is. So if you are in 4s, I think you can see here, if you're in 4s, you actually start with the 3d. That's what the n minus 1 means. And then the n here matches the n here. But then we go to n minus 2. Why do we go to n minus 2? Because what you don't see is that this here starts this here. So this really expands out. And then we have 6s. And then we have 4f, and that's the n. So if n equals 6, it's n minus 2. And that's where the 4f comes from. So this is a good picture or image to maintain, hold on to if you're having problems understanding the n. But it's really not as difficult as it may seem. We just haven't looked at this stuff in a while. Like I said, I think you learned it in 110, and you really haven't, I think, had to really focus on it again. And we're going to look at it again in this section. So I found this online to kind of give a good explanation of what you need to do in these sections. But mainly we're focusing on this one. So this is the one, and some of this one too, the F's, which we really don't really ever talk about. But in this case, we're going to start talking about some of them, but we're mostly focusing on the D's. So for instance, the NS2, so if we look at something like, excuse me, we have something with an argon 4s3d. So if we look at, that's a 4s, and then it goes into this here, and it does the abbreviation for the noble gas. That's what the argon is what you see here. And then if we go and look at another one, we see a 5s. So in this case, I'm losing here. 5s, that means that krypton would be this here, and then it's 5s and 4d. So don't let these overly confuse you. They're really not as confusing as they may seem right now. It's just we haven't been looking at these. Okay, so in general, the valence d orbitals of a transition metal of a period n are located in the n minus 1. So if you're looking at n minus 1 is what the d orbitals are going to be. N will stay the same, so if you have a 4, that's fine. But then you have to bring it into this formula, so it would be a 3d. If you have a 6, Then you have to bring it into this formula, and it's a 5D. So remember, it's always one less. And that's because you can see it starts down. So 3 is here, but the 3D is down here. So it starts one past that one. All right, so now we're going to look at electron configurations. And there are some, remember, there's two that are a little weird. And it is chromium and copper. And that is because we do not fill them up the same way as we do the others. So if you see, they both start with an S1 instead of an S2, because if this was how we normally had learned them, or you should have learned them this way in 110, I actually did not learn them this way. I had learned them the old-fashioned way, where this is 4S2 3D4 and this is 4S2 3D9. That's how I learned them as a student, or maybe I'm remembering a false memory, but that's how it was for me. Why do we have them this way? Because when you show them in electron to orbitals in this way, you can see that it fills all the electrons up here and only leaves it with one here as the same as here, and it leaves. So this is lower in energy by doing this than having moving one out and putting it here and leaving just 4 orbitals here. Moving one out here leaves 9, and it's not as stable as spreading them out completely. So that's why these look like that. So these are the two that will change. And remember this, because I haven't put together the homework yet or quizzes, but I like these. So just keep that in mind if I get an option. Here's electron configuration for the d orbitals. So I included these so you can see how they are set up. And I highlighted or bolded the ones that are the special cases of these. Well, but you can see the numbers increase and decrease. See, there's no 9 here because that's the special one. This would be a 4, but it's a 5, so we've changed these two. And then here's more of them. So I've included these in just in case this is helpful as a reminder to see these, especially with Fs. Fs get kind of weird because we probably haven't worked on Fs in a very long time, if ever. Okay, so now we're going to write electron configurations, and there is something different than the way that you have been learning how to do them. And so you're going to have to change the way you learned it, or maybe you did learn this. We are going to start making these ions. So they are no longer going to be stable atoms, but ions, which means we have to take electrons away. But we're not going to take the electrons away from the D. They're going to be taken from the S first. And that's where things might get a little weird for you for some. So the outer S electrons beginning with scandium. So once we get to scandium, then we're going to lose these electrons from the S and not the D. And you may want to ask, well, where is scandium? Okay, so let's go back and find scandium. Scandium is atomic number of 21. So let's go back even further, and hopefully I can find, and it's right there. So it's right away, we're going to lose the S's first before we lose the D electrons. And that's what we're going to learn how to write right now. So here is some examples. So during, again, the outer S electrons are transition metals. So transition metals, this is the only thing we're talking about here, are lost during ionization before the outer D electron. So let's take a look at some examples. So we have cobalt, and here's electron configuration for cobalt. But when it goes to cobalt 2, the S's are gone. The S is gone. And you can actually write the S out if you needed to, but you'd have to put a 0 here, if that helps you understand what you're doing. But in this case, it's sometimes easier just to write it, and it's actually the proper way is to write it without the S. But if you need the S in the beginning, you could write 4S and a 0, and it's still correct because you're not counting the electrons there. But we're taking the S's from, we're taking the electrons from the S's before we take them from the D orbitals. Iron, here is the full abbreviated electron configuration. And then we remove 2 electrons, which makes it iron 2. And as you can see again, we remove the S orbitals. So this here is not correct. You see how this is 4s2 3d6? This is 4s2 3d4. These electrons were taken from the D orbitals, which is exactly going against the rule of what I'm saying. It's from the S's first before D. So S before D. And in iron 3, we have also, we've taken the S orbitals out. However, now we've taken one of the D orbitals, which is exactly the hierarchy that we need to do, the rules that we need to do. We need to take S first before we take from the D's. Okay, so start by writing the electron configuration and as normal, and then remove the outermost electrons to form the ion. So in this case, write it out normally. Write it out as you would. Don't confuse yourself. Make it as easy as possible. And then if you needed to take the 2 electrons are in the s orbital. Take these out first, and that you would see are the two outer s electrons, and this is the new electron configuration for the ion. Okay, that if you recall that a few transition metal groups have electron configurations that don't follow the periodic table predictions. I don't remember what that's about, but don't worry about that. Sorry. I don't know what that is talking about. I don't remember seeing that in your book. I should have caught that line. I would have removed it. Okay, so, and anyways, I'm not going to give you anything off the hand anyways that if I haven't covered or it's not in the book. Write the ground state for electron configuration for zircon. So we get the first, the abbreviated krypton. Second thing is that we're going to, that's the noble gas, and then we're going to fill out the rest. So we know that this is a 5th period, so we figure we get the 5s, 4d, and then we fill in the electron configurations for it. So let me just start over. Count down the periods to determine the outer, that would be the n on the outside of the periodic table. Subtract 1 to obtain the quantum d, so we have the d. If the element is in the 3rd or 4th transitions, include n minus 2f up to 14 electrons. Okay, so now we're going to count across the row to see how many electrons in their neutral atom. And it has zircon has 4 more electrons than krypton. So we have 5s2, 4d2. Now we want to make, this is asking for the ground state electron configuration. So we have it in its ground state electron configuration. However, if we were asking for it to be oxidized, then we would then remove from the s first before the d's. All right, so now let's look at, write the ground state electron configuration for cobalt. So this is an ion, but we're going to write the ground state configuration for it. So we look at the noble gas abbreviated, and then we count down again, do the same things that we did, and we follow the same rules. So depending on if F is included or not, we have those rules there. So cobalt is in the 4th period, so we add the 4s, 3d, and then we count across, and we can tell that it has 9 electrons. So we're going to add 9 electrons to the s orbitals and 7 to the d orbitals. And that's it. We have our ground state electron configuration. Okay, so now, well, I think I just repeated this. Did I just repeat this? Cobalt, what did I do here? Okay, I realized what I did. I copy and pasted onto a new slide, and I copied some of the information over, which I didn't want. Now, so what we're doing is we're ending it here. But if you needed to do an ion, then this is what I was talking about. You have to remove the 3. So where do you remove the 3 from? Well, you first remove from the s orbital, so that's why I say you can write a 0, and then you remove 1 from the d orbital. And you either have this configuration or you have this configuration. Okay, so give the electron configurations of the following atoms. These are not step by step, they just have the answer, and I've just supplied the answer. So hopefully once you look at these, try to look at them, do them, and then check and see if your answers are correct. But you notice that in these here, we don't have the s orbitals are missing from these. Okay, why aren't there, so now we're going to actually start looking at atomic size. And I think this slide, why aren't the 3rd transition atoms bigger? I was having some problems putting this one together, so I should have fixed this, but now I've started recording and I don't know how to stop and edit. So we're just going to go through and come back to the slide. So atomic size, and it also means radius, depending on what book you look at. So for main group we would have covered this in 110, and as you can see, as you go across the periodic table, it gets smaller, and that has to do with effective nuclear charge. Because yes, you're adding more electrons, but you're also adding a proton. And the smaller ones have a higher hold on those electrons, keeping them closer together, where the larger ones do not. And as you go down, you're increasing in a level. So that's also expanding it out in a level, which means that the hold on those are not as strong. So these have a higher ability to lose those electrons, where these do not like to give up those electrons at all. But something weird happens in the transition state metals. They don't really change very much. As you see from here to here, even these 2 columns, they're a big change. Here to here, there's a big change. But when you start on this side, there really is not as a big change as you see. And then if you look in between, some of them even match in size. And even across here, there's a little weird one, but they also don't change in size very much. So what's happening with the transition metals? So Again, generally they decrease from left to right across a period atomic size or radii, and that has to do with the electrons being shielded. The greater the pull on them, they can hold on to them. But in the middle, there are some, it's different. Okay, so why is there not a big change in the atomic and the radius? And that has to do with the s and d orbitals themselves. So when we're looking at transition metals, we normally, in most cases, except for a few exceptions, the s orbital has 2 electrons in it, and then what happens is that all the the electrons are added then out to the d, which has a lower quantum number and is lower in energy. So because of this, this is added. These added electrons shield the outer s electrons, and that means that the transition metals don't experience as pronounced a contraction of the radii as the way it is in like p in the p block, for instance. So what am I saying here? I'm saying that the d orbitals, because remember they are lower in energy. So if you're in 4s, but you're actually in 3d for the d electrons, the 3 puts them in a lower energy, and that shields the 4s orbitals, the electrons away, and so there's not as much as they can't pull them as close. So that's why the radii does not change as much, because of, in a sense, the d electrons are shielding the outer 2 s electrons from the nuclear charge, and it's not allowing it to pull the way it would for a p block. Okay, so now there's also a trend that when we're looking down a column, and so the atomic radii of main group elements, remember, these increase down a given group, and this also follows with transition metals, but only in the sense of period. So if we look at period 4, which is 3D, and period 5, 4D, the difference in radii between the period 5 and 4D and the period 6, 5D is minimal. And the reason the radii does not change that much is similar to why the radii changed a little across the D block period. So beginning with, it says here, beginning with element 57, electrons are placed in the 4f orbitals, which are lower in energy than the 5d and 6s, and do not shield the outer electrons as well as sp and d orbitals. So that poor shielding of 4f subshell and current and the increase in nuclear charge, because remember, as you go across, you're also increasing an electron and a proton, that results in the 6s electrons experiencing stronger effective nuclear charge. So there is a difference in, excuse me, there's not a difference. So simply saying, the 4f electrons are doing what I previously stated with the 5d, with the d orbitals with the s. They do not shield the electrons as well. And because, well, this is kind of opposite though. This is, they're not shielding as well. So because they're not shielding as well as the sp or d orbitals, because again, now I just contradicted myself. Let me start over. I previously discussed how the d orbitals protect the s orbitals and they don't have the greater pull. Now it's the opposite. The 4f electrons do not shield the outer electrons as well as sp and d orbitals. So that allows the 6s orbitals to have a stronger pull, and they're pulled in, they're contracted in, or they're pulled in to the radii, and that is why you don't see a big increase in. There is a trend, but it's not that much. It's very minimal, is what they're trying to say between 5 and D. So this the resulting lack of the expected increase, because it's not increasing as much as it should be, because we're going into a level of n equals 6, you would expect it to be larger, but because the f orbitals are not shielding it, they're being pulled in. That is called the lanthanoid contraction. So I have a few examples here. We can take a look at this here. The atomic radii of all the transition metals are very similar. So you can see there's a small increase in size down a column. So you see the green is the third row, red is the second row, and first row is here. The third transition series atoms are about the same size as the second, and that's because there's not really a big change. That's why when we learned atomic radii, the transition metals were never discussed really, and that's because it gets kind of complicated when you're first learning how to do this. The lanthanoid contraction is the decrease in expected atomic size for the third transition series atoms that come after the lanthanides. Remember, we have, and it's not shown here, remember we also have, we always focus on the periodic table here, but there are others down here that are actually included in the periodic table. So this is the lanthanoid contraction, and that's because of we expect the atomic radii to increase, but it's not increasing, and that is why, because the 4Fs are not shielding it the way that we expect it to go. So here I just expanded this out more so you can see the atomic radius and the group number and having to do with the periods 4 and 5. And if you see 6 at the end, 6 is actually below 5. So it's actually gone down in atomic radius compared to 5. Okay, so which element has a larger atomic radius, iron or tungsten? So I thought I had put it here. Sorry. If we look here, you can see that iron is here. And then when we look, tungsten is here. So which one has a higher? So we have a period 4 here, and we have a period 6 here. So the atomic radius, there is still differences in sizes. You can see here by looking at it. But, so here's a group number 8, and here's group number 5. So tungsten still has a larger atomic radius in this case. So we can compare atomic radius between these. It's just, there's not going to be as drastic of a change as, I mean, because even these are pretty close, and, you know, in some cases you can see they overlap. All right. Okay, so predict whether Y, I forgot what Y is, ruthenium or cadmium has the largest atomic size. So let's take a look at what we have here. Here's Y. So we're in period 5. And then if we go down, we have here, this is ruthenium, and then we have cadmium. So they're all in period 5. So they're all in period 5. This is a group 3. So group 3 is still larger than when we get to group 12. So in this case, Y, I can't remember what it's called. It is going to be Y is the first element in the series and expected to have the largest atomic radius, which it does. That is a period 5 transition metal. All right, so ionization energy. Okay, so if you remember what ionization energy is the energy needed to make that atom an ion. And like the trend with the main group is that the energies, remember main group elements is what I'm talking about. The first ionization energies increase from left to right. And that is the same for transition metals. They increase from left to right. That means the energy needed to remove an electron increases. So you need more energy as you go across. So from left to right. And that is due to an increase in effective nuclear charge. Remember, that's holding everything close to it. So as you go across or go next, go on down a row, you are increasing the proton, you're also increasing the electron, and that is allowing a greater pull on that. So that's the effective nuclear charge. But in the same way that the atomic radius does not decrease as expected, the same thing happens with ionization energy. It increases not as much as we would expect, and that has to do with the d orbitals. So going from left to right, remember electrons added to the d orbitals shield the s electrons, so by the similar amount. So this means that the increase in ionization energy is not as expected. So the ionization energies of main groups generally decrease down the group. The ionization energies of the periods 4 and 5, which is meaning 3D and 4D, are relatively similar. I'm going to show you right here. Let me go through and I can, this is the page. So when we look at period 6, which is 5D, transition metals have a higher first energies than those in periods of 4 and 5. And that is because of the lanthanoid contraction. So that renders the atomic, that has to do with the atomic radius. So remember, the atomic radii of 5D transition metals is similar to the radii of 4D transition metals. And period 6 metals experience a stronger effective nuclear charge because the 4F orbitals do not shield as much. So they have an effective nuclear charge than those in period 5. So electrons in the 6 s orbital are more difficult to remove than would be expected. Okay, so period 6, remember the 4F orbitals do not protect it as much, so it pulls them in, so there's a stronger pull on those period 6 metals. Okay, so here's a graph of the ionization energy. The first row of ionization energies of the transition metals slowly increases across the row. Green is the third row, red is the second, and blue is the first. And you can see they all kind of are sort of near each other, and then they start to expand. And then the blue and the red are sort of stay together, but the green is a little bit off. So the first ionization energies of the third transition row is generally higher than those of the first to second rows, and that indicates the valence electrons are held more tightly. So remember, the higher the energy, the higher the value of ionization energy, it means more energy has to be put in to remove that electron. So in this case, that means that these valence electrons are held more tightly, and the trend is opposite to main group elements. Because if you remember, going down a group, I think I have it here. I do not have, of all the graphs I showed, I didn't bring it here. Ionization energies are less, the more you go down a column, that means that it takes less energy to remove those electrons. So if you think of group 1 and group 2 metals, it's easier to remove those as you go down, like in, if we're looking at period 6 compared to period 5, and that has to do with also the levels. But in this case, we're looking at the third row, and it actually takes more energy to remove an electron than from the second and the first row. Where if you consider group 1 and 2 metals, like sodium and lithium, and so as you go down, it's easier to remove them because they get bigger and bigger. Okay, so I just expanded it out again so you can see that, and this is nice because this actually has the name of them so you can see which ones they are. Okay, so electronegativity. Electronegativity of transition metals slowly increases across a series, so except for the last element in the series. So that's exactly what you're seeing. You're seeing how they slowly increase. There's a little dip here, except for the last one. The last ones go down. Electronegativity slightly increases between the first and second rows, but the third transition row atoms are about the same as the second. Again, this is a trend that is opposite to the main group elements. Okay, so remember the main group elements, there's generally an increase from left to right across a period and from bottom to top. Remember, fluorine is the most electronegative atom. And the transition metals do increase, but they increase very, very small. There's a very small increase when you go across the D block. And going down a group, there's an increase in electronegativity between period 4 and period 5, and that has to do with the small change in atomic radius between those periods of the transition metals. However, there's little to no difference in electronegativity between the elements in period 5 and 6, and I like that the slide says it's not easily explained. So you just need to know that, but you don't need to know why. So I made this bigger so you can see how the trend goes with these, and then let's look at some problems. So predict whether titanium, rhodium, or iridium has the highest first ionization energy. So if we look here at the first one here, and we can pull them out. So I had them all pulled out, now I don't remember. So we have this one, which is a period 6. We have this one, which is a period 5. And right here we have a period 4. So if we look at this and we're looking for the ionization energy, shows that period 6 transition metals tend to have a higher first ionization energies than periods 4 and 5 transition metals. Iridium does indeed have a higher first ionization energy than rhodium and titanium, which is exactly what it shows here. So now in the second one, we're looking at which is the most electronegative. So let's see where we can find these. And it just says, I gave you the answers on this page, but it doesn't really say why. Okay, so on this one, we have iron, which is a period 4. We have, I pulled these all out and now I can't find them. Palladium, which is right here, which is a period 5. And then we need copper, which should be, where's copper at? It is right here. Okay, so when we look at these, remember electronegativities of periods 5 and 6 transition metals are similar and tend to be higher than those of period 4 transition metals. So iron and copper are both, here we go, iron and copper are both period 4 transition metals, while palladium, which, where is it at right here, is a period 5 metal. So palladium is more electronegative than any of the period 4 transition metals. And that's what it shows here. Okay, so now we're going to go on to oxidation states. So here we're going to discuss oxidation states, and here's a picture of the first row transition metal. So this is, excuse me, this will be a period 4. So when we look at this here, I want to point out some trends. And we look, if we oxidize as a loss of 2 electrons, that would be the s orbitals. So that's where you can see almost everything loses an s orbital on this case. Manganese is the one that has the highest oxidation state, so it can lose anything between 2 and 7. And then the red means the most common, and the brown is the less common that you can see here. So there's some interesting things about this. Again, when you see a +2 oxidation states, that's the result of losing both electrons in the outer s orbital. That's common for these elements. And that's because the s orbital electrons are relatively easy to remove. Now, the oxidation states peak halfway, and that is manganese. So this is halfway between the d orbitals, and decreases again towards the end of the block. And that is the major reason for the decrease is an increase in effective nuclear charge, which makes it harder to remove d electrons. And remember, so as we're going across, we're still adding electrons to this, and as we are increasing across this, and that means more electrons, more protons. So there's a greater effective nuclear charge. So it makes it harder to remove those d electrons. In other words, going from left to right across a d block, the outer d electrons of the transition metals are not as well shielded from the positive charge of the nuclei. So that's why you can see that the oxidation goes down, because you can't pull those electrons off as easy. So that's why if you look at something like nickel and copper, it's really common to have a oxidation state of +2, but it's really difficult to get it to +3, either one of these, and that has to do with the effective nuclear charge, where it's holding on to this more. So it's not going to give those up very easily. And when we look at transition metals of the 5th and 6th periods, they possess 4d and 5d electrons and are able to actually achieve higher common oxidation states. And you can achieve oxidation states of a +8 in ruthenium and osmium, but these tend to, the period 4 ones tend to be the most common ones that we tend to work with. But yes, we can do that with some of the other ones, but it's easier if we focus on, something. These are what we tend to use over and over again. Okay, so review. Most transition metals lose their outer s electrons before their d electrons when they're ionized. Transition metals near the middle of the d block tend to have the highest stable oxidation states. The shielding effect of lower quantum number d electrons prevents transition metals from experiencing the same radius contraction across the d block that the main group experiences across the p block. The filling of electrons into a poorly shielding 4f and the concurrent increase in nuclear charge, so it's simultaneously this happening, results in 5d transition metals having approximately the same atomic radius as 4d. This observation is known as the lanthanoid contraction. First ionization energies of transition metals increase across a period, but do so drastically different than the main group elements. Due to the lanthanoid contraction, 5d transition metals have higher ionization energies than 4d, and the electronegativities of transition metals increase from left to right across a period and from bottom to top within a group, but the increase is less drastic